13.3, the fundamental theorem of line integrals, video 10. This will be the last video in the series. You're probably thinking, thank goodness. But I wanted to do an example of a vector field in 3 dimensions, since everything's been just 2 dimensions, but most everything in our world is 3-dimensional for you future physicists and engineers. Let's consider this really long vector field. F of x, y, z equals, as the I component function, 2xy plus z squared plus y sine of z plus 3x squared, plus, as the j component function, x squared plus e to the z power plus x sine z plus 2y, plus, as the k component function, 2xz plus y e to the z power plus xy cosine z plus 1 over z. Assuming f is conservative, it is, because I built this function by starting with a potential and finding its gradient. Find its potential. Again, the whole purpose of finding the potential in this video, in this chapter, in this section of this chapter, is it makes evaluating a line integral straightforward if you're integrating a conservative vector field and you know its potential. You simply have to evaluate the potential at the terminal point of the curve and the initial point of the curve and subtract the results. Oh my goodness, how are we going to find this potential? By remembering what it means to be a potential. This first component function is the partial derivative of the potential with respect to x. This second component function is the partial derivative of the potential with respect to y. And by the way, I'm calling the potential lowercase f like we've been doing. And the third component function is the partial derivative of the potential with respect to z. So what we're going to do is basically what we did in the last example. Integrate to recover part of the function, take the derivative to connect it to another partial derivative, but now we'll have to do that process twice to get through all 3 partial derivatives. So let's start with the partial derivative of f is equal to 2xy plus z squared plus y sine of z plus 3x squared. Since this is the partial derivative with respect to x, let's start by integrating this with respect to x. So the integral of 2xy plus z squared plus y sine of z plus 3x squared dx. That will recover the function, sort of, on the left, and now we integrate everything with respect to x. The integral of 2xy with respect to x is x squared y. The next 2 terms are essentially constants because they contain no x's, so they're antiderivative, you just stick an x on it. So xz squared plus xy sine z. Something's not right here. Something's not right. Actually, it is correct. Never mind. In my mind, I was going through how I set this up, so forget what I just said. We're integrating with respect to x, and the integral of 3x squared is x cubed. Now, we can't just tack on a constant, because think about what would have disappeared if we took the partial derivative with respect to x. What would have disappeared is anything containing y's and z's only. In other words, if there were any parts of the original function, any terms that did not contain an x, they would have vanished when we took the partial derivative with respect to x. So what we have to append is some function, we'll call it g, not just of y, but of y and z. Any function that did not include an x would have vanished, so we have to assume it could have been any function containing only y's and z's. All right, so how are we going to find that? Well, let's continue by connecting what we know to the next partial derivative with respect to y. So let's take the partial derivative with respect to y and see what happens. Going across, the partial derivative of x squared y with respect to y is x squared. The next term contains no y term, so it would disappear upon partial differentiation with respect to y. The next term, the x sine z is like a constant, so the derivative of a constant times y is just that constant. So we get x sine of z. X cubed with respect to y would disappear, so it's gone. And then over here we have the partial derivative of g with respect to y of yz. Okay? So now that we know what the partial derivative of f with respect to x looks like, f with respect to y, we know what it looks like here, and we also know what it looks like here. So now we can equate the two. X squared plus x sine z plus the partial derivative of some function g of yz with respect to y is equal to this guy. So it equals x squared plus e to the z power plus x sine of z plus 2y. Let's look for anything that cancels. The x squareds cancel. The x sine z's cancel. Okay, so this means that the partial derivative of g with respect to y of yz is equal to e to the z power plus 2y. Okay, so what can we do with that? Well, we can integrate that with respect to y. The integral of the partial derivative of g with respect to y of yz dy is equal to the integral of e to the z plus 2y dy. Okay, let's see what this gives us. This gives us the original g function, g of yz, is equal to, now remember we're integrating with respect to y, so z is like a constant. So the integral of e to the z dy is y e to the z. The integral of 2y is y squared. Plus, we still don't pick up a constant, and here's why. This is a function of y and z. When we take its partial derivative with respect to y, anything that contained only z would have disappeared. So it may be more than just a constant, it may be a function of z, because it would have disappeared upon partial differentiation with respect to y. We know it doesn't contain any x's because it was just a function of y and z. So there may be some function of z, we'll call it h of z, that completely vanished when this guy got differentiated partially with respect to y. So now we kind of know what the g function looks like, and what we can do with it is embed it back inside of what our function looks like up here, This is what we're looking for. And now we know something a little bit more about this function. It has that form. So that means that our function f is now of the form x squared y plus xz squared plus xy sine z plus x cubed. Again, I'm just rewriting what's kind of circled in blue. It's circled on one end, square on the other. Plus g. And we know more about the g function now. It's y e to the z power plus y squared plus some unknown function of z. So how are we going to recover that unknown function of z? By taking advantage of the third partial derivative that we haven't taken advantage of yet. We know that the partial derivative with respect to z is equal to that. So let's take the partial derivative of what we know about f with respect to z. This disappears. The derivative of xz squared the partial derivative of xz squared with respect to z is 2xz. This has a z in it. The x and the y are constant. The derivative of sine is cosine. So the partial derivative of xy sine z with respect to z is xy cosine z. This has no z, so its partial derivative with respect to z is 0. This has a z, the y is like a constant, so the derivative of y e to the z is y times e to the z. Since the derivative of e to the z is e to the z. The derivative of y squared, partial derivative of y squared with respect to z is 0, so it's gone. And now we take the partial derivative of h of z with respect to z. But this is just a function of z. It contains no x's or y's. So its partial derivative is its ordinary derivative, h prime of z. So now we've got the partial derivative of f with respect to z is this mess, but we also know that it's this mess. So at this point, all we have to do is compare. If you'll notice, if we equated these two things, one boxed in green, one underlined in green, the 2xz's would cancel, the y e to the z would cancel, the xy cosine of z would cancel. The only thing left here would be h prime of z. And the only thing left here would be 1 over z. And hopefully you remember that the antiderivative of 1 over z is the natural log of the absolute value of z. We'll just say the natural log of z. I know it technically means an absolute value. Oh, plus a constant. Now we pick up our constant. So now we've got the last missing piece of the function that's kind of hidden right here. I know this is a big mess. I really wish I had more room to go straight down without having to go over and sideways and in corners and stuff. But if we put it all together, our function is hiding right here. And the only missing piece is the h of z, which we just found. So, therefore, our potential function f of x, y, z is equal to x squared y plus xz squared plus xy sine of z plus x cubed plus y e to the z. Have to clear some room here. I was right here, plus y squared, plus h of z, which was the natural log of z. I'll go ahead and put it in absolute values, technically it should be, plus some constant. Now that seemed like a lot of work to recover the potential, but imagine doing the line integral without it. If we did a line integral, we would have to take the derivatives of all these, substitute x, y, and z equals whatever the functions are in the parametric function defines the curve over which the line integral is being evaluated, and then have fun with that, especially with all the e's and the trig functions. I want to do one more thing with this that we haven't done. In physics and engineering, you will have a lot of what are called initial value problems or initial condition problems. If you've had differential equations, you probably know what I'm talking about. Basically, it gives you enough information to calculate the c. So for example, if f of 0, 0, 1 is equal to 4, find the c. Well, that's easy. Just plug in zeros for the x's and the y's and 1 for the z's. Why did I say 1 for the z and not 0? Because of the natural log. Can't put 0 here, but you can put 1 and the natural log of 1 is 0. So let's see what disappears. Everything is 0 except the z's. So you're gone, you're gone, you're gone, you're gone, you're gone, you're gone, and you're the natural log of 1, which is 0. So we get 0 plus c is equal to 4, and our constant is 4. Or whatever the initial values are, the initial condition is. All right, well, I know this was a lot of theoretical stuff and not that many examples, but yeah, like I said, you're on a path towards theoretical math, whether you wanted to or not. For those of you in the physics and engineering going in those directions, I would recommend reading through 13.3 because the author does make several allusions to physics and engineering applications. I'll just cite them real quick. On page 774, example 13, is an example of finding the work done by a gravitational field. It's not really that difficult because they talk about the function as the vector field as the gradient of a potential function, so they're just illustrating the fundamental theorem of line integrals. Let's see, where else? On page 775 in the paragraph below Theorem 3, they briefly talk about the physical interpretation that the work done by a conservative force field as it moves around an object, as it moves an object around a closed path of zero. So for example, the work done by the gravitational field on the sun and other bodies acting on the earth, the total work involved is zero once the earth makes a complete revolution around the sun. Zero work for all that? Crazy. Let's see, where else? Let's see, in example 4 on page 778, they have an illustration of a vector field. They don't really give a real physics or engineering application to it, they just got a picture of a vector field. And on the bottom of page 779, which really kind of shines some light on why we use the word conservative vector field and potential function. They do an example about conservation of energy. And at the end, actually it leads to the law of conservation of energy. Talking about kinetic and engineering potential energy. So for those of you who are more physics and engineering oriented, I strongly recommend on the bottom of page 779 to read the section and actually follow, and if you want to work out the math by hand, the section about conservation of energy, which shines a lot of light on the use of the words conservative and potential in these contexts. All right, I hope I didn't turn your brains too much into scrambled eggs, but at this stage of the game, whether you're going math, physics, or engineering, this is par for the course. I'll be honest, as you get into your junior and senior years in graduate school, you'll look back on this stuff and go, man, I wish things were as easy as they used to be. All right, hope you're enjoying these videos. You guys stay safe. Oh, that was a long video.